All right, guys, this is our last experiment for the semester. So you're getting it early and hopefully be finished early. We're doing simulated radioactive decay, and we're using dice to represent the nucleus. So what we're going to do basically is we're going to throw a bunch of dice into a box, and there's a certain probability that we're going to use the number 1 indicates that the dice has, quote, decayed. And so there's a certain probability that that occurs. Since these dice are six-sided, not 20-sided like the lab says, obviously that probability is 1 out of 6, assuming all of the dice are, fair dice. And so therefore the probability to lambda is 0.167, 1 over 6. And the number that decay should be proportional to the number that are there. And so the d and dt, he does this in the lab right up. Excuse me. D and dt is proportional to n, so that proportionality is lambda. And since it's decaying, you have fewer later, and so it's going to have a minus sign. So basically, you start off with the concept that d and dt is equal to minus lambda times n. And basically that results in an equation that says n is equal to some initial number that you started with at time t equals 0 times e to the minus lambda t. If we take the natural logarithm of both sides, we get the natural log of n is equal to natural log of n naught minus lambda t. So if we plot log of n versus t, we should get a graph that is a straight line and it has a slope of minus lambda. This would be the y-intercept, and so that's going to be at time t equals 0. Of course, the log of n naught equals the log of n naught 0, so that kind of makes sense. So what we're going to do, we're going to get the data. Actually, we've already got the data, as you can probably see, and then you're going to simply plot this on Cartesian graph paper or Excel, obviously, and what you're going to plot will be log of n on the y-axis and t, which is the throw number, on the x-axis. So that represents t. So each throw could represent a second, could represent a year, or anything like that if we're talking about radioactive decay or something like that. Obviously, the numbers we're working here, we start with 270 dice. That's very small. The statistics aren't going to be real good here, and you can probably already see that in the data. If you've got 10 to the 12th nuclei, then you get much better statistics, and you get a very predictable outcome. So pretty easy lab write-up. You're just going to basically do this graph, find the slope of it, and compare that to 0.167. And then the half-life is the time that it takes to get to n naught over 2. And you can find that, of course, by, this would be the log of a half. And so that's the log of 2 is 0.693. The log of a half would be minus 0.693. And so t log of a half, a half-life is equal to 0.693 divided by lambda. Of course, our theoretical lambda is 0.167. Just look at your graph, and wherever you get to n naught, where n is equal to n naught over 2, so that'd be 135, and that's going to be your half-life. And compared to this number here, I think that's 4 point something. I don't know what it is exactly, but you can do the division. So James and I have already done all the heavy lifting here. We've thrown the dice 20 times. We've pulled out all of the ones, and this is the data. So you guys have that there. I don't think we'll even show you how we did the experiment. I mean, it's pretty straightforward. We put the dice in a couple of cups, tossed them into a box, and then pulled out the ones. If you have any questions, you can email James or myself. This lab will be due the week before the last week class. So what is that, the week of April the 6th, I think it would be. No?
12th. So today is 24th. So I think it'll be the week of the 12th. right?
Week of the 12th, that's the last week of class, so. Is that okay?
We'll figure it out.
Okay, get with James on that, but get it done as soon as you can, is the best deal. I know you got a lot of things going on. It's, as we all do, it's been strange times, so, work with James or send me an email and we'll try to get this figured out. All right, thank you, have a good afternoon.